From the topic instrumental methods, we are going to study the third point, that is Lamberts Beers law. So in this point we will study the statement of Lamberts Beers law and the derived equation and the problems which are given in this topic. Let's begin with the statement. Now see here, when a beam of light is passed through an absorbing medium, so in this case the absorbing medium is a solution, a part of that light is absorbed and the rest is transmitted. Means what? We are passing a beam of light through the solution and a part of light is get absorbed and the rest is get transmitted. Now see here, the amount of light absorbed depends on the concentration of solution and the length traveled by the light through the solution body. So how much amount of light is absorbed by that solution is wholly depends upon the concentration of that solution and the length by which the light travels. So these two points are important: the concentration of solution and the length of the length traveled by the light through the solution. So on these 2 points, how much amount of light is absorbed by will be calculated. So this is a law given by a Lamberts Beers. So this is the combined law. So now see the statement again. The amount of light absorbed depends on the concentration of solution and the length traveled by the light through the solution body. The quantitative relation between the amount of light absorbed, concentration and the length of the absorbing medium is given by the law, that is Lamberts law and Beers law. So there is a relation between the amount of light is absorbed and the concentration of the solution and the length of the absorbing medium. So by correlating these 3 points, the law is put forwarded by these Lamberts Beers and the combined law, that is Lamberts Beers law. So one by one we will start the Lamberts these laws. So firstly we will start what is meant by Lamberts law. Now see here, so according to this law, and this law is stated in 1760, and what is the statements here? Equal fractions of the incident light are absorbed by successive layers of equal thickness of the absorbing medium. So this law states that the amount of light which is absorbed by the successive layer of equal thickness of the absorbing medium is totally depends upon the thickness of that layer. So how much fraction of light is absorbed is wholly depends upon the thickness of the absorbing medium. So see this figure here, the absorption of light by medium, figure 2. So they have drawn the square here. So at the bottom here x is equal to 0 and at the right x is equal to L. So this is the length of that absorbing medium. At the middle here the line is there. At the left I0 is nothing but it is the intensity of incident light initially. So the light which are going to incident on that absorbing medium, so the intensity initially is I0. When it travels through the absorbing medium and it passes from that solution, at the overright side there is a symbol, that is IT, that is transmitted intensity of transmitted light. On the upper side at the left C is equal to 0 and the right side C is equal to C. So this is the concentration. And the middle part C here, on the arrow there is a small letters, that is DC, that is a small part of that solution, that is the concentration, and at the below dx is there. This is the small length of the absorbing medium. Now see here the explanation of this figure. In figure 2, a layer of thickness dx absorbs a small amount of di of the incident light. So we are passing a light of intensity I0 through the absorbing medium. So dx is the small thickness of the absorbing medium absorbs that light, and the amount of light absorbed by that small part of the absorbing medium is di. So this small amount of light, that is di, is absorbed by the small thickness, that is dx of the absorbing medium. The fraction di by I, the fraction di by I is proportional to the thickness of the layer, that is dx. So what is the fraction? Di by I means di is the small amount of light absorbed by that medium, and I is the intensity of the light. So they have given the equation, negative sign of di by I is directly proportional to dx. So di by I is nothing but the small fraction of light is absorbed by the solution, and how much light is get absorbed is totally depends or is directly proportional to the small fraction, that is the thickness of the absorbing medium, that is dx. We may write it as, or di by I is equal to, the negative sign is written on right side, minus the proportionality constant is k1 dx. So di by I is equal to minus k1 dx. This is the equation number 3. Now see here, where I is the intensity of the light incident on the layer, I is the intensity of light incident on the layer, k1 is the proportionality constant. The negative sign indicates, now see here what it indicates. The negative sign indicates that due to absorption of the incident light, the light is get absorbed by the solution. Because of that, intensity of that light is get decreased as it passes through the absorbing medium. When light travels from left to right through the absorbing medium, on the right hand side, whatever the light is get transmitted, the intensity of that light is lower than the intensity of incident light. Therefore, when it travels from the medium, the intensity of that light is get decreased. Therefore, in the equation number 3, they have written that is minus di by I is directly proportional to dx. Negative sign indicates that the intensity of light when traveling through the absorbing medium, it decreases when it passes from that solution. In the next line, see here, if I0 is the initial intensity of light incident on the absorbing medium of length L. So I0 is the initial intensity of light which is incident on the absorbing medium of length L. So this total length is L, and IT is the intensity of the transmitted beam. IT is the intensity of transmitted beam. Then we are going to integrate the equation number 3. So I0 is the intensity of light which is incident initially on the absorbing medium. So the total thickness or length of the absorbing medium is L. IT is the intensity of transmitted beam. So now see here, the equation 3 is going to be integrated. So di by I is integrated from IT to I0. So I0 is the initial intensity and IT is the final intensity, is equal to k1 integration of x to 0 x to L. So from small thickness to bigger thickness, and they have written there at dx. So when integrating this equation, we will get the equation log to the base e IT divided by I0 is equal to minus k1L. So L is nothing but the length of the absorbing medium, IT is transmitted light, and I0 is the intensity of incident light. Or we may write this equation as, we can change the negative sign on the right side. So log to the base e I0 by IT. In the initial second equation, in the second line, IT by I0 is there, but in the next line, so it is just reversed. I0 by IT is equal to k1 and L. So negative sign is get vanished. So converting to base 10, we get the equation 2.303 log to the base 10 of I0 by IT is equal to k1 into L. So this is the Lamberts equation, Lambert's law equation, where the intensity of light which is incident on the absorbing medium, whatever the light is get absorbed is wholly depends upon the uh, thickness of the absorbing medium. So the equation is 2.303 log to the base 10 I0 by IT is equal to K1 into L. So this is the equation number 4. So this is nothing but the Lambert's law. So again I will just revise within a 1 minute. So according to this law, whatever the fraction of light is going to be absorbed by medium is depends upon the thickness of the absorbing medium. If more the thickness of the absorbing medium, more light is get absorbed. If smaller the thickness of the absorbing medium, the minimum light is get absorbed. So this is given by this equation, that is 2.303 log to the base 10 I0 by IT is equal to K1 into L. So the next equation is Beers law. This law is also put forward in 1852, and it states that equal fraction of incident light is absorbed by successive layers having equal concentration of the absorbing medium. So in Lambert's law, whatever the amount of light is going to be absorbed is depends upon the thickness, but according to the Beer, whatever the light is going to be absorbed by the absorbing medium is also depends upon the concentration of that absorbing medium. So in the figure we know that di, that is a small amount of light, is absorbed by the layer, that is dx layer, having the concentration. Suppose that layer has a concentration small on the right top side. See on the figure, dc is there, so this is nothing but small concentration, that is concentration of that small portion of that absorbing medium. So the fraction di by I is proportional. Now whatever the fraction of light is going to be absorbed is directly proportional to the concentration of the absorbing medium. Therefore the equation is minus di by I is directly proportional to dc. So again we will write this equation as di by I is equal to minus k2 into dc. So this is the equation number 5. So if you see the equation number 3 on the upper side, the equation is di by I is equal to minus k1 dx, and if you see the equation number 5, the di by I is equal to minus k2 into dc. In the equation number 3, whatever the amount of light is going to be absorbed by the absorbing medium is directly proportional to the thickness of the absorbing medium, but according to the Beer's law, whatever the light is going to be absorbed by the absorbing medium is depends upon the concentration of that absorbing medium, where I is the intensity of light incident on the layer, K2 is constant. The negative sign, just similar to the K1, indicates that due to absorption the intensity of light is get decreased as it passes through the absorbing medium having total concentration C. If I0 is the initial intensity of incident light on the absorbing medium having total concentration C, IT is the intensity of transmitted beam, then we are going to integrate the equation number 5. So this equation number 5 is going to be integrated. See here, integration from I0 to IT, di by I is equal to K2 from smaller concentration less concentration C0 to CC, and integrating the concentration term. So by integrating this equation, we are getting log to the base E IT upon I0 is equal to minus K2 into C, or log to the base E, we can reverse the left side, I0 by IT is equal to K2 into C. If you see this equation here, equation number 4 and equation number 6, you will realize that the equation is just similar, but only the difference is that in Lambert's law there is an L, that is thickness, but in Beer's law there is the term concentration. So 2.303 log to the base 10 I0 by IT is equal to K2C. So this is the Beer's equation for absorbing light. So if we combine these two equations, that is equation number 4 and equation number 6, then the new law is there, that is the combined law, Beers-Lamberts law. So we will see the Lamberts-Beers law, that is a combination of Lamberts law and Beers law. So this law states that, now see this third line, equal fractions of incident light are absorbed by successive layers of equal thickness and equal concentration of the absorbing medium. According to this law, now see here, whatever the fraction of light is absorbed by the solution or absorbing medium is depends upon the first point, that is thickness of that absorbing medium, and second, it depends upon the concentration of the absorbing medium. So the equation 4 by the Lamberts law, it is 2.303 log to the base 10 I0 by IT is equal to K1 into L. According to the Beers law, the equation is 2.303 log to the base 10 I0 by IT is equal to K2 into C. So we get, if you combine this equation, then we will get 2.303 log to the base 10 I0 by IT is equal to A into C into L, where, now see this equation, A into C into L, where A is constant called absorptivity of the absorbing medium, C is the concentration which is in mole per dm cube, and L which is length of the absorbing medium which is in centimeter. So the above equation can be rewritten as log to the base 10 I0 by IT is equal to A upon 2.303. So this 2.303 from the left side is taken at the below of divided of A 2.303 C into L is equal to epsilon. So that symbol is epsilon C into L. Now see, so this is the equation number 7. So what is equation number 7? Log to the base 10 I0 by IT is equal to A upon 2.303 C into L. So where epsilon is nothing but it is A by 2.303 is called as molar absorptivity of the absorbing medium. So A is only the absorptivity, and epsilon is nothing but it is the molar absorptivity of the absorbing medium. So this equation number 7 is the combined equation for this Lamberts Beers law, log to the base 10 I0 by IT is equal to A into CL or A upon 2.303 CL or epsilon C into L. So there are 2 points, absorbance A and transmittance T. So now see here, what is absorbance? Log to the base 10 I0 by IT is called as absorbance of the absorbing medium. Transmittance, the fraction IT by I0, that is how much fraction of light is get transmitted. So that fraction IT by I0 is called as transmittance, capital T, of the absorbing medium. So A absorbance is nothing but log to the base 10 I0 by IT, and transmittance is nothing but IT by I0. So the percentage transmittance is percentage equal to IT by I0 into 100. So the equation 7 can be rewritten as, so log to the base 10 I0 by IT is nothing but A, capital A. So A is equal to log to the base 10 I0 by IT is equal to, if you reverse this numerator and denominator, so we can write it is negative log to the base 10 IT by I0. So IT by I0 is nothing but transmittance, therefore there is written as negative log to the base 10 capital T, so that is transmittance, is equal to epsilon C into L. So this is the equation, that is A is equal to epsilon CL, or we can write as A is equal to negative log to the base 10 of T, or we may write as A is equal to log to the base 10 I0 by IT. So this is the equation number 8. So from equation 7 we again write as I0 by IT is equal to 10 raised to epsilon c into L, or IT is equal to I0 10 raised to minus epsilon c into L. The intensity of light IAB is which is absorbed is given by the equation IAB is equal to I0 minus IT. So how much amount of light is absorbed is depends upon the intensity of initial light and intensity of transmitted light. If you differentiate these two, we will get the intensity of absorbed light. So I0 is minus IT, just we have written in the last page, I0 into 10 raised to minus epsilon CL. So IB is equal to I0 in the bracket 1 minus 10 raised to minus epsilon CL. So this is the equation number 9. So just we have seen what is mean by Lamberts law. So according to this law, when equal fraction of incident light are absorbed by successive layers of equal thickness of the absorbing medium, and according to the Beers law, whatever the light is absorbed by the absorbing medium is directly proportional to the concentration of the absorbing medium. So the Lamberts law is equation number 4, which is 2.303 log to the base 10. I0 by IT is equal to K1 into L, and the equation number 6, that is 2.303 log to the base 10, I0 by IT is equal to K2 into C. So these two equations are from the Lamberts law and Beers law respectively. Again, if we combine these two equations, then we will get the new theory of equation, that is Lamberts Beers law equation. So according to this law, whatever the light is get absorbed by the absorbing medium is directly proportional to the thickness and also the concentration of that medium. So if you see this equation number 7, then log the base 10 I0 by IT is equal to epsilon c into L. See the equation number 8, A is equal to log to the base 10 I0 by IT, or A is equal to negative log to the base 10 T, or A is equal to epsilon c into L. And finally the last equation, equation number 9, I0, whatever the amount of light is absorbed, so how much intensity of light is absorbed is calculated by this equation. IAB is equal to I0 in the bracket 1 minus 10 raised to minus epsilon CL. So epsilon is nothing but it is the molar absorptivity according to equation 8. So equation 8 is A is equal to epsilon c into L. So in terms of epsilon, we can write this equation as epsilon is equal to A by c into L. So C is, if suppose the concentration of that absorbing medium is 1 mole per dm cube and the length of absorbing medium is 1 centimeter, then epsilon is equal to A. Why? Because C and L becomes 1, A by 1 is A, therefore epsilon is equal to 1. Hence the molar absorptivity epsilon is the absorbance of an absorbing medium. Now see, it is defined by using these lines. Molar absorptivity, that is epsilon, is nothing but the absorbance of the absorbing medium, because epsilon is equal to A when it is epsilon is equal to A when C is equal to 1 and L is equal to 1. Hence the molar absorptivity is the absorbance of the absorbing medium whose concentration is 1 mole per dm cube and length is 1 centimeter. So when the concentration of the absorbing medium is 1 mole per dm cube and length is 1 centimeter, then in that condition epsilon is nothing but the absorbance of that absorbing medium. The value of molar absorptivity depends on the nature of absorbing species in the solution. So the value of that epsilon is depends upon what species are present in the solution and the solvent in which the species is dissolved and the wavelength of radiation. So epsilon has a unit dm cube per mole per centimeter, dm cube per mole per centimeter. So A is nothing but absorbance, C and L are the concentrations, So in terms of this equation, the unit of this epsilon is dm cube mole per centimeter. So whether this Lambert's law or Lamberts Beers law is valid to all solutions or not is explained in this next point. So validity of Beers Lambert's law. So the Lamberts Beers law is strictly applicable to dilute solutions only. So if the solution is highly concentrated, that solution cannot obey this Lamberts Beers law. So this law is only strictly applicable and obeyed by the dilute solutions whose concentration are below 10 raised to minus 2 molar. Means if the concentration of the solution is below 10 raised to minus 2 molar, then and then only that solution obeys Lamberts Beers law. If the concentration of that solution is more than 10 raised to minus 2 molar, then the Lamberts Beers law will not be obeyed by that solution. From equation 8, if you know that equation 8, A is equal to epsilon Cl. So equation 8, according to which absorbance is proportional to the concentration of solution and transmittance is inversely proportional to the concentration. So absorbance is proportional to the concentration, transmittance is inversely proportional to the concentration. If we increase the concentration of absorbing medium, absorbance is get increased and transmittance is get decreased. Therefore, if more the concentration, more the absorbance, more the concentration, lesser is the transmittance. So if you see this figure A, figure B, figure C, so it is explained in below here. Now see here, as shown in figure 2A, a straight line. So see the left hand side graph, the solid line is there at the middle. A straight line graph passing through the origin confirms that the absorbing species obeys Lamberts Beers law. So this law obeys the Lamberts Beers law. The dotted curve Roman 1 indicates a positive deviation from the law, whereas Roman 2 indicates a negative deviation. So in the figure A, if you see the straight line, solid straight line from the middle, if you get the graph like this, then the Lamberts Beers law is obeyed by that solution. If there is a dotted line, that is I dotted line is there in the graph, then that there is a positive deviation. If you obtain a second, that is Roman second dotted line graph like that, then there is a negative deviation from the Lamberts law. So why the deviation occurs from the Lamberts Beers law? So let we see here. Deviation from Lamberts Beers law are of two types. When the observed absorbance is greater than expected value. If suppose the observed absorbance, if it is greater than expected value, it is called as positive deviation. If more the absorbance, if the solution absorbs more light, then there is a positive deviation. And if the absorbance is lower than the expected value, then there is an reverse case is there, that is negative deviation occurs. So this deviation can be broadly classified into three categories. One is the real deviation, second one is instrumental deviation, third one is the chemical deviation. So one by one we will see what exactly it means to us. So one, real deviation. The linear relationship between absorbance and concentration of solution is observed only in dilute solution. Means A is directly proportional to C is only observed in the dilute solution and does not hold true at concentration which is above more than 10 raised to minus 2 molar. If solution concentration is more, the law will not be obeyed. If concentration of the solution is lower, then the law will be obeyed. The molar absorptivity epsilon depends on the refractive index of the absorbing medium. So the epsilon depends upon the Ri, that is refractive index of the absorbing medium. The refractive index changes when the concentration of the solution is get changed. At high concentration, the changes are considerable, but at concentration below 10 raised to minus 2 molar, they can be neglected. So if the concentration of the absorbing medium is lower than 10 raised to minus 2 molar, then the Lamberts Beers law is get obeyed. The second deviation, the instrumental deviation, the light incident on the absorbing medium should be strictly monochromatic. Otherwise, deviation from Lamberts Beers law is get observed. Means whatever the light is going to be incident on the absorbing medium, that light should be a monochromatic. Monochromatic means single colored, means single wavelength light. If you pass through the absorbing medium, then and then only this law is get obeyed. So monochromators are used to produce monochromatic beams which are absorbed to the maximum extent by the absorbing medium, that is lambda max. In last lecture we have seen what is the lambda max value and why it occurs to the solution. The third one, the chemical deviation. So why the solution does not obey the Lamberts Beers law? The reason is because of the chemical deviation. Now see here, the Lamberts Beers law is not obeyed if the absorbing species undergoes dissociation or association, or if reaction occurs in the solution. If suppose we are passing a light through the solution, if the solution is get dissociated, or if the molecules from that solution is get associated, or if the reaction takes place in the solution, in that cases only the Lamberts Beers law will not be obeyed by that solution. The molecules of the absorbing species should remain as simple molecules in solution and should not undergo any change in the molecular condition. Means whatever the absorbing species which are present in the absorbing solution, that is in that solution, that species should not change their structure. Then and then only the Lamberts Beers law will be obeyed by these absorbing species. Also, the absorbing species should not react with the solvent. Means whatever the species which we are going to be analyzed, so that species should not interact with the solvent. If they are interacted with the solvent, the reaction will happen and the solution will not obey the Lamberts Beers law. They have given the example here. The best example in this case is of potassium dichromate K2Cr2O7. See here, chromium 6, the Roman 6 indicates that the chromium is in the 6 oxidation state. So chromium 6 exists totally as in K2Cr2O7, and in alkaline medium it is into K2CrO4, as the color of the two ions are different here. So in case of K2Cr2O7, the chromium is in plus 6 oxidation state, and in K2CrO4, so the chromium in both of these compound, the color of these ions are get changed. Because of that, due to different color, the lambda max value of these two compounds are different. So at an intermediate pH, the chromium 6 added will partly exist as chromate and partly as a dichromate. So this chromium at intermediate pH, it behaves, that is, it is in K2Cr2O7 form, or it is in K2CrO4 form. So because of this two ion formation, the color of this solution is get changed. The measured concentration will correspond to either chromate or dichromate depending upon the wavelength used and not the total chromium added. The amount of total chromium added is known, but how much of it exists as chromate or dichromate is not known to us. Means we know the total amount of chromium in that solution, but we does not know how much amount of chromium is exist in chromate or in dichromate. This leads to a deviation from the Lamberts Beers law. So this is what we have seen today in the lecture. Uh, the theory of Lamberts Beers law. So in the first case, Lamberts law is seen. Second point, Beers law, and the combined law. So A is equal to epsilon C into L. So the absorbance is totally depends upon the concentration and the path length of the absorbing medium. And we also seen what is meant by molar absorptivity. Why the solution does not obey Lambert's law, Beard's law is also seen here. And what are the that is deviations? Because of that, the law is not obeyed by the solution. So there are three deviations. One is real deviation, instrumental deviations, and chemical deviation. Just we have seen. In the next lecture, we will see the examples related to the Lamberts Beard's law.